So we'll start talking about with the sort of the size of SLAC when it was first built. When SLAC was first built, how big was it relative to other science projects at the time?
SLAC was going to be the biggest basic research project ever. It was, at the time, $100 million. And I looked up the inflation numbers from 1962 when the contract was signed till now is almost a factor of 8. So the actual machine was 120 million. And today's money, that's building a $1 billion thing from an empty lot. There wasn't anything here. As I said, it was the biggest basic research project ever done by the U.S. government. They'd done a lot bigger projects, but they weren't basic research projects.
Great. And obviously, because it was so big, they had a code name for it when they were planning it. What was the code name and what did it signify?
It was called here Project M for Monster. And Monster because it was so much bigger than the baby that existed on campus. I came here in 1956 as a postdoc, and I came here to use the linear accelerator that existed on campus. It was about, I think if I remember it right, 200 or 300 feet long, not 10,000 feet long. And it had an energy that was about 700 million electron volts compared to the 18 billion electron volts when SLAC turned on. SLAC's energy has increased over time, but at the turn on, when they pushed the on button, it was 18 billion, and its antecedent was much smaller. So it was called the Monster.
So when they were building SLAC, what were some of the unique construction challenges they faced?
It was very long. And one of the problems that was fought out very early was who was going to handle the conventional construction. The government was not, I would say the government was kind of skeptical that a university could do it. But the university's position was that if they didn't do it, they weren't going to build it. So that was argued out, and the university was given the authority to run the whole project, including the tunnels, the bulldozers, building 10,000 feet of accelerator tubes, supports, the first ever laser alignment system in the world, the big klystrons. Stanford and the SLAC organization did it all.
And then one of the sort of the unique things that people always seem to get a chuckle out of is that, you know, when they were building they were planning Highway 280 around the same time, and they had to do something pretty unique with SLAC so that they wouldn't have to shut down the accelerator. Can you sort of tell that story or talk about that a little bit?
Well, we were building the accelerator, and one of the things about the accelerator when it was running is you didn't want it to shake. And if you were going to be building a highway bridge over it, it wasn't the cars running across the bridge, it was the construction machinery that was going on that was going to really shake the ground. And the feeling was that you wouldn't be able to run the accelerator. So they built the bridge early, and it had a very delightful byproduct because I believe it was from the present Page Mill Road up to what is now Sand Hill Road that they built the whole thing. But there were no highways at either end. And I used to take the kids out, and we'd go bicycling on this lovely 6-lane superhighway, carefully paved, going over hills, gorgeous views, and not a car in the place to worry about. Delightful. So anyway, the state highway people were really very good.
What was important about finding experimental evidence? Why was that so important to fundamental physics?
Well, what had been going on in the 50s and early in the 60s was the continuing discovery of new states. People, when the first were being discovered, they felt these were new elementary particles. But as the book that contained the properties of these got thicker and thicker and thicker, it became clear to everybody that these weren't elementary particles. They had to be something built up from more fundamental entities. Originally, in the theorists, the fundamental entities were mathematics. They called them various symmetry principles, group theory, and various mathematical models predicted a collection of states. And the states were built up out of smaller entities. They were, let's see, George Zweig was one of the fathers of this, but the one who won the race for naming rights was Murray Gell-Mann. He called them quarks. Zweig called them aces. Quarks won over aces. And now you had a mathematical structure which said certain properties would turn up in particles if you constructed them according to this mathematical model. But even Gell-Mann said that it was a mathematical model and didn't necessarily mean that these were real entities. The first of our big experiments, what's called the deep inelastic electron scattering experiment, showed that, in fact, these things were real, that the protons had a substructure, neutrons had a substructure, and they were made of smaller entities, and those smaller entities had the properties that were predicted by this mathematical model. So instead of being a mathematical convenience to talk about quarks, you now had some real entities. There's a very interesting story about that. This was a big laboratory, and lots of people wanted to use it. And we had a program committee. And the program committee was scientists mainly from outside. I think there were 12 members of the program committee, and only 2 of them could be from SLAC. And if you wanted to use the machine, then you put in a proposal. And you put in the proposal, and they would look at all the proposals, and they would pick out the ones that should run. So the proposal was put in, was a proposal to do what's called the inelastic electron scattering experiment. But the program committee said, no, you've got to do the elastic scattering experiment first. The leader of that group was Richard Taylor. I don't know if you've interviewed Dick. No, but he's got this big bushy beard now. He looks like a biblical prophet unless he's decided to shave. And Taylor's attitude was, once they've approved the experiment, we are going to determine how the apparatus is set up. And so they did the inelastic scattering first. And they got some very strange results. And they took this to one of our young faculty, J.D. Burkane, known as BJ, who visits now and again. And he put together the evidence in a different way that showed what BJ called scaling. And this scaling said that as you went up in energy, the cross-section should behave in certain ways, and they did. And that scaling was also characteristic of a quark model, too. And in fact, it is the combination of BJ's telling them how to organize the data, and the data itself that was a demonstration of the existence of quarks.
So I remember listening to your 50th anniversary speech, and you were talking about the difference between the early end-station experiments and then the types of experiments that you could perform at SPEAR. And you had a really good analogy. You were talking about bowling balls and pins. If you want to use that, that's great, but it would be cool to hear about the difference between those early experiments and how they functioned, and then the first collider experiments at Spear.
Okay. One of the things that was going on in high energy physics, even earlier than the start of SLAC, was what they were going to do to get the energy of the beams up higher. Relativity made what I called the interaction energy much smaller than the beam energy. So if you collide a beam with a target at rest in the lab, the actual energy available to make new things is much lower. And one of the analogies I like to use when I'm talking to people, I don't know how useful it is now, is bowling. Years and years ago, bowling used to be very popular. Now not many people bowl, but if I was talking about bowling, I would ask people to think about the bowling balls and the pins at the end of the alley. And the bowling ball comes rolling down the alley and it hits the pins and the pins fly all over the place. And the bowling ball barely slows down. It has a huge amount of energy, but not much of it gets transferred to those pins. So if you think about rolling two bowling balls at each other, you wouldn't like to get something stuck between them when they hit. In the modern times, bowling balls aren't so good, but I can talk about clashes between a big highway truck and a Volkswagen. The same sort of thing. The highway truck is going to barely change, and the little car is just going to get smashed to rubble. So there was, starting just about the time I was getting my PhD, this business of what could we do to do something about this? And the idea of colliding beams came up. Instead of the bowling ball hitting pins at rest, what we're going to do is turn this into collisions of two bowling balls. So if you think about numbers, one of the numbers that was bandied about is if I took two accelerators of 20 billion electron volts energy each and made the beams collide, I would get the same interaction energy as if I had one accelerator of 1,000 billion electron volts colliding with a target at rest. So making two at 20 compared to one at 1,000 was much cheaper. And so the question was, were we going to be able to get the energies up very high? How big would the colliding beam machines be? How big would a conventional machine be? So one of the things I did as a homework exercise to amuse myself while I was a graduate student is I took the biggest machine you could think of. I put it in orbit. And it was at geosynchronous orbit up at 25,000 miles above the surface of the Earth. And it went all the way around the Earth. And it was 150,000 miles in circumference. And that machine on a fixed target would deliver about 1/10 the energy that you're getting out of a Large Hadron Collider at CERN. But it would cost 1,000 times, 1,000,000 times more. Just think of 150,000 miles of magnets around the Earth. So I got interested in that. And when I came out as a graduate student, one of the people who had been talking about colliding beams, Gerard K. O'Neill, physics professor from Princeton, known as Jerry, came out with the idea of building an electron collider. We knew a lot less about accelerators than we know now, and injecting into a proton machine was very hard, but injecting into an electron machine was very easy. And it turns out that the reason is the emission of synchrotron radiation And you know, since you're doing things about SLAC, that synchrotron X-rays are a very big deal in science. So a group was put together which consisted of O'Neill and one of his graduate students at that time, and me and one of the senior researchers here, Carl Barber from here, me, the postdoc. And the four of us went on to build the first real colliding beam machine ever built. And our argument was we not only were going to make a demonstration of colliding beams and find out what its problems were, but we were going to do a test of the theory of quantum electrodynamics at an energy which you simply couldn't get to any other way. Panoski, our first director, was very well connected in Washington, and he sold this idea to the government. The first question, who was going to fund it? And at that time, this was actually before SLAC. This was a little accelerator on campus. It was funded by the Office of Naval Research. And the Office of Naval Research put up the money for us to build it. And so the first colliding beam machine was born. And interestingly enough, it had a circulating current of 0.6 of an ampere, and that was not exceeded until the B factory was built at SLAC in the 90s. 0.6 of an ampere held the world's record for a very long time. So anyway, that demonstrated the colliding beams worked, and there was a slow switch. Everything now in high energy physics is colliding beam machine, all of them. And I think I'm probably the last of the pioneers who's still around. I was young when I got my PhD. I was 25 when I came out here. And all the others in the business were more senior, and Bernie Gittleman, O'Neill's postdoc, and me, we were the junior types, and I've outlasted all the rest of them.
So speaking of colliding beams, obviously we'd like to talk about the J-psi and the discovery of that. So to begin, I guess, what is the J-psi and how is it important to how we think of fundamental physics?
I want to turn your question around because you had two questions. One was, what is the J-psi? And then what's your next question there?
It was, how is it important to fundamental physics?
I want to turn these around and talk about what we were trying to do with the colliding beam machine that we built here. So on campus, the first ever colliding beam machine was built. Colliding beam machines became very interesting, but in the beginning it was the electron-positron colliding beam machines that excited the most interest. And with an electron and a positron collider, you could make particles collide, electron and positron, particle and antiparticle. They could annihilate, and I always describe this as a little fireball in a tiny region of space with a huge amount of energy, and from that could come out anything that you could produce. So what were we looking for with the energy? Anything. What we were looking for was something about the strong interactions. We had all of these particles still, and remember, SPEAR started early. It started on the proposal before SLAC was running, before the quarks were found. And so we were looking for what I called in the first proposal something about the relative structure of all these mesons. So you could produce a pair of pi mesons or a pair of k mesons. What was different about those things? Clearly they had very different properties, but if you made them, what was different? Unfortunately, we got sidetracked by the Vietnam War. The budget for physics had been going up like crazy, with Sputnik going up in the Eisenhower administration, a growth of fundamental physics, the first $100 million fundamental science laboratory and all of that. And we were ready to go in '64, but now the budget started to flatten out. And so we had to keep trying and trying and trying and simplify the machine and make it lower cost and all of that. My partner in all this was John Rees. John Rees had come to us from an Electron Synchrotron lab in the East, in the Harvard MIT Synchrotron, and he was my partner in Accelerator crime here as we were doing things. And he and I made this more and more simple, but I drew the line at one place, and that one place was the existence of the magnetic detector. I felt that you had to look at everything, and you had to know the momentum and energy of all the things that came out, and you had to know the correlations between them. In 1970, we finally got the go-ahead to do it, only after some, I would call it maneuvering by the Department of Energy, and I never knew why the man who was the controller of the Department of Energy, named John P. Abadessa, became fascinated by this. So Panofsky was in Washington, and Abadessa calls him into his office. This is Panofsky's story. I was not there. And Abadessa says, "Professor Panofsky, are there any permanent buildings in this project?" And Pief was a little bit baffled at the line of questions, but he knew something was going on. And he said, "No, sir, there are no permanent buildings." Professor Panofsky, is this project going to last for more than 5 years? And Pief says, "No, I think we'll be able to do it in 5 years." Well, then Professor Panofsky, this is not a line item construction project and doesn't have to be specifically approved by Congress, but can be built out of the ongoing budget of your laboratory. And that was the go-ahead. We were really ready to go, and we put that machine together in 20 months. 20 months from the first papers going out to bid to turning the machine on. And then we started looking at what we were looking at. Now it turned on in 1972. We already knew about quarks. We knew about substructure. There are all sorts of interesting questions. And the first thing we did was take a scan as a function of energy with this machine and see what was new was there. And the thing that turned up in '74 was something that was not allowed by the then version of the Standard Model, including the quarks. There were 3 quarks, and only certain kinds of particles were allowed. And the thing that we found wasn't one of them. It was forbidden. It couldn't exist in the old model. Well, not only we found it, but 3,000 miles away on the East Coast, Sam Ting and his group found something which looked very much like it. They found it a different way. We took electrons and positrons to produce things that flew apart. He took something else. He took protons to collide with protons to produce something that decayed. But he also found something that was not allowed to exist, which had exactly the same mass as the something at Stanford that wasn't allowed to exist. And that was the thing that caused what was named by the physics community, not by either of us, as the November Revolution. November 11th, 1974, was the day that Sam came out here for a meeting of our program committee. And he and I met in Panofsky's office. And we found, to our surprise, that we seem to have found the same thing. So things happened rather fast after that. We actually got the papers into the same issue of the Physical Review letters, and I think it was 3 or 4 weeks. It would take months to get anything through this system now. He called his the J, and I don't know why. I called ours the psi, and the reason is that it was pretty clear that the properties of this unallowed particle were very much like the properties of other particles which had already been found. And the thing that we did is we looked at the table, and all those other particles were lowercase Greek letters. And there were only 2 of them left. Psi was one, and upsilon was the other. And I didn't like the sound of upsilon. I thought psi sounded better, so that's the one we picked. There the 2 papers were back to back, and in the same journal, J and psi. And to settle the argument, since they're published simultaneously, it was given the name of J/psi, and the reason his was first is because he got his into the Physical Review office half a day before we did. So his was first in the journal. That's why it's J/psi.
Go ahead. All right.
Okay, so the November Revolution made me famous and made Sam Ting famous. And 2 years later, we both shared the Nobel Prize. And as far as I was concerned, I was beginning to get a little restless. Did I want to keep on climbing the same mountain, doing the same sort of things? So I did a bit, but I got increasingly restless. And as Panofsky neared retirement age, he decided I was supposed to be his successor. So in 1982, I agreed to take on the job of head of the technical division, except I didn't want to be called the associate director of the technical division. I wanted to be technical director of SLAC, and he agreed. 2 years later, he retired, and in 1984, I found myself as director of the lab. Panofsky had been a terrific mentor for me. He was the person I came out to work with when I came to Stanford in the first place, and I learned a lot from him. I took over the lab. I had already learned a lot more about running places and doing all sorts of things, and there I was with a lab, and the question that every director has to deal with is, what are you going to do to stay on the frontier? So with SLAC, we had a problem that I could see, and that problem was the size of the site. And given the size of the site and what you could expect to happen in the size of accelerators and colliding beams over the next couple of decades, it wouldn't fit here. So what were we going to do to remain on the frontier? And that gives the director of the laboratory a real job, because the director doesn't know everything about all the fields, but the director's got the job of sorting out a whole bunch of options, and you've got to mine the brains of your faculty, your staff, and your users. And so that's what I did, and one of the things I did was to greatly expand the synchrotron radiation program. When I became director, SPEAR was also the synchrotron light source. We had let the X-rays out with, let me think for a minute. It doesn't matter. I had a proposal from Seb Doniak and Bill Spicer Spicer from electrical engineering, Doniak from applied physics. They said, let the X-rays out of SPEAR and we will revolutionize condensed matter physics. Well, I wasn't a condensed matter type. So I picked two people who were. I wasn't director yet. The machine was not even finished at the time. And I took one of them and said, is the physics right? And I took the other and said, if we do what they want, can we do it without getting our collider in trouble? The one who I asked about the science said yes, they were absolutely correct. They could revolutionize it. And the one who I asked about the accelerator said, yes, we can let this beam out. It isn't easy, but we can do it. And so we did it, and that was the start of SPEAR. So when Doniak and Spicer came to me to talk to me about letting the X-rays out of a colliding beam machine, they said they would revolutionize condensed matter physics, and I said, why? And their answer was that your X-ray beams are 1,000,000 times the intensity of anything we can get from an X-ray tube. And with that kind of intensity, experimental studies are possible that you simply can't do with an X-ray tube. That's when I asked Ed Garwin, who was SLAC's only solid-state and condensed matter physics, whether these people were blowing smoke at me. And he came back and said, no, they're not. 1,000,000 times the intensity is the right number, and it's truly revolutionary. And you know that already because the colliding beam things have 1,000,000 times the intensity at high energy that you can get otherwise. Jerry Fisher was one of our accelerator physicists. And one of the things that was a worry was letting these things out because the windows had to be thin. And for colliding beam operations, we had to have a very good vacuum. And if that window had broken and let things up to room temperature air with a lot of water and other such stuff in it, our machine would be off for at least 6 months before we could get it back operating. So Jerry and the engineers, he pulled together a group, and they came back and said, we can do this. It's not exactly what they want. We made them put in a double window. So if one of them went, there was another one that would go. That cut the intensity by a bit, but after all, they had a factor of 1,000,000. So if it was only a factor of 500,000, they could still revolutionize things. So they started off, and their focus was on solid-state physics, and they delivered. And then it got broader and broader and broader. Keith Hodgson, a chemist, revolutionized structural biology because though a chemist he was, he came out here and developed a structural biology program where using the X-rays and diffraction patterns to find out the detailed structure of complicated biologically important molecules. That is a huge operation now. So huge, in fact, that the National Institutes of Health paid half the cost of the last upgrade to SPEAR. And they don't like to put money into things like accelerators, but that was a big enough deal, so they did that. So it has been a great success, and it's kept getting bigger and bigger and bigger. So here is '84, and the synchrotron radiation program had more than fulfilled its promise. It had not only revolutionized condensed matter physics, but it now had a role in biology and geology and environmental sciences and what have you. And so I started backing them in looking at major expansions. And expand they did. The DOE forced Stanford to move the synchrotron radiation program, then called SSRL, in as part of the SLAC contract. It had become the biggest R&D contract, and everybody was very nervous. The faculty was nervous. They didn't want to do it. They thought they would get swallowed. And I could look at them and said there was no way they could grow as they ought to without having the resources of a big lab. So I went and arranged a conspiracy with the Department of Energy. And that conspiracy was that the Department of Energy would say, look, you don't have any choice. The Office of Management and Budget says we can't keep this separate, and the Office of Management and Budget has said you cannot have two management and operating contracts at a single laboratory. So you two have to get married. And get married we did, and I started funneling them money to expand the facilities at Spear and to begin the design of what became the X-ray laser, LCLS. That's interesting because it's an example of something that directors have to do. I didn't know what you could do with an X-ray laser. I never liked LCLS, but there's some battles you can't win, and I kept trying to say, guys, call this an X-ray laser. And they said, no, it's going to be a LINAC coherent light source. And so they came up with a notion about an energy for the X-rays. And I said, I want you to bring together the potential users. I want you to have a workshop on what is the right energy for this facility. Not something I'm going to tell you, but it's got to be something that the community of potential users gets behind too. They did that, and that workshop called for a much higher energy than they were originally thinking about. And we started the design on it. It didn't get realized until the Dorfan and Drell here as director. But it got started and it got put in the queue before I stepped down as director. The other thing was on the particle physics side. What could we do because the site was limited? So we looked at an international project for a linear collider. 3 labs, KK, the Japanese labs, DAISY, the German lab, and SLAC. We all worked together on what you could do with a new kind of electron-positron colliding beam thing. That hasn't been realized as a special project yet, but we did the first one here. First one, the SLAC linear collider. It wasn't really 2 LINACs. It was 1 LINAC with 2 beams and a tennis racket-shaped head that could bring them in a collide. Never mind the technical reasons. It could work at the original energy. The original energy was 100 billion electron volts, more than 5 times the original SLAC energy. And build it we did, and it went on, and this international collaboration went on. When I stepped down as director, the international collaboration had not yet come up with a design. But one of the other things that happened that got brought to me as a potential was a space mission, the Fermi satellite, as it's called now. That is a creation of the physics department and SLAC people. Peter Michelson from the physics department, Elliot Bloom from here, and one of our senior staff were the ones who dreamed this thing up. And this one, again, looking at the community and the potential users, was a clear winner, and the director's job is to sell those things. So off I went to Washington, and I didn't have any trouble with NASA. The head of NASA at the time and his chief scientist thought this was absolutely terrific. The problem was the DOE. It took a long time to get the DOE to do it, and it wasn't until Dorfan was director that the DOE finally signed on the bottom line. But the R&D had been going forward, and NASA was behind it. It was nuclear was going to go ahead. So here are two examples of things where they're not in the director's own scientific experience, but you've got the job of trying to sort out all these jobs and see what's going to keep you on the frontier in the future. So the lab, when I first became director, had about 600 outside users. When I turned over this to my successor, we had 3,000 outside users. The facilities clearly were attracting science. We, with the X-ray laser, became the world's leading laboratory in photon sciences. The rest of the world is chasing us. And the crew here now, with the new version of what's called LCLS2, we are certainly at the minimum in photon sciences going to be among the world's leading laboratories in 2025. The satellite is up there, it's going around, it's on its second 5-year extension. NASA, for these things, wants to look at what they're producing and decide whether to keep going. So with our satellite, it is not a matter of running out of rocket fuel, because it doesn't use any. But it's a matter of, is it going to run out of interesting things to do? My own guess is it'll get another 5-year extension and may or may not go on any longer than that. So one of the things is what's next in what I call astroparticle physics. And there we have LSST, where SLAC is the lead on the camera. Camera is a 3 billion pixel CCD camera, which is not a big deal because the last experiment that was built for high energy physics was a 300 million pixel CCD camera. This is a factor of 10 scale up. As far as the CCD goes, we know how to do it. We know how to read it out. We know how to do all that stuff. Making this camera with its mechanical tolerances is a very big deal. But the technology in the LSST camera is technology developed in high energy physics. The technology in the Fermi satellite is also technology that was developed for high energy physics. And now Chi Chang has got the job of saying, where are we going to be in 2030? That's 15 years from now. So we know where we're going to be in 2025 on the photon science side. We're going to have the new X-ray laser with the superconducting linear accelerator and all this sort of stuff. I don't know what else is in the minds of our faculty and staff and users, but these ideas don't just come from the insiders. They come from everybody who uses it. And of our 3,000 users, 2,500 of them are not from Stanford. So we have a big community, and I turn this over to Chi Chang. Jonathan Dorfan closed the deal on Kavli, and he also finally got the deal closed with the DOE on the Fermi satellite, on that part. Persis has broadened the scientific mission of the lab, and Persis oversaw the completion of the first X-ray laser. Chi Chang has already gotten the first of his jobs done, that is for 2025 with the new thing. LSST will come on in the early 2020s, but what's the next one? And that's his job to figure out.